Hi, I'm Adam Field. This is my presentation on AI models class when trained on recursively generated data. Me and my partner chose this issue because LLMs are increasingly prevalent online today, leading to the increase in importance of this issue. Getting right into it, this paper is on what happens when generative artificial intelligence, like LLMs, are trained on exclusively previously generated data. Um, this leads to defects, specifically low probability events disappearing and high probability events being overestimated. Um, this is called model collapse. We're going to understand what model collapse is, the math behind it, the significance of it, and a way to prevent it. So, what is model collapse? Model collapse is what happens when you train an LLM, but in your training data set, there is generated data from another AI that already exists. Uh, this causes misperceiving reality over many generations of doing this similar thing. So let's look at this image to understand further. So an AI generated this image on multiple types of dogs and their labels. It's very detailed. There's a lot of different types of dogs, but notice that the Golden Retriever is the most common dog on this list. There's two of them compared to one unique one of the rest. Uh, so we train a new LLM on this data set and ask it to produce the same image. But this time, the high probability event, the golden retriever, is starting to dominate the probability distribution. And so the low probability events, corgis and bulldogs, disappeared. It's also losing accuracy. So it flipped the Dalmatian and the golden retriever here, and it also lost all the names, which is a lot of information. Um, then we do it all again. We train an LM on this image and ask it to generate this image. Um, and what occurs is the high probability event has completely dominated the probability distribution. All the low probability events have disappeared. We call those tails. And now the high probability events have polluted reality. Um, and then we do it a third time, same thing. And what occurs is model collapse. This is when they're not even dogs anymore. They're just smudges. And it's all the same thing. So the most probable event got started to dominate the probability distribution. And then it started to lose so much accuracy that it's no longer even dogs. It's just nonsense, right? So this issue is caused by three different sources of error: statistical approximation, functional expressivity, and functional approximation error. That just basically says that our statistics isn't completely accurate. Our numbers can only hold 64 bits, and small, tiny errors like that one in the code of our LLMs uh, cascade over multiple generations to cause a larger error and ultimately model collapse. So, in this paper, they did two experiments to understand model collapse farther. They did the first experiment on 5 generations, and they lost 8 perplexity. Uh, 8 perplexity is a lot of information. It's akin to going from a detailed diagram of dogs to smudges, right? And then in the second experiment, they did 10 iterations, but this time they preserved 10% of the original unpolluted data. So 10% of the textbook information about dogs, right? And this resulted in a minor degradation of perplexity. These two experiments show that the degradation of perplexity is unavoidable, no matter how much you preserve data, unless you preserve 100% of it, but we're assuming we don't do that. Um, and then it also shows that a small 10% of data being preserved significantly increases the amount of time that you can the amount of times that you can train a AI on previously generated data. Um, so the figures in this paper show what model collapse is. This figure A is what model collapse is. On the right here, there is a we start with data. It's a flow chart. We start with data, and it says that probable events are overestimated and improbable events are underestimated. So the corgis and the bulldogs are being underestimated, and the golden retrievers are being overestimated. And then the model is created based off of that, and the probable event starts to poison reality. The golden retriever starts to replace the low probable events, and the tails start to shrink. The corgis start to disappear. And over again, this happens until they're all just smudges, just like that picture we had. Um, then in Model B, or in Figure B, this is an example, or this is the results of the first experiment that I just described above. Um, so on the right here, this graph shows that we start with the real data and we train an AI on it, and it has 60 perplexity points. Then we train another LLM on the previously generated data from this generation, and it drastically loses its perplexity points. So we see this happen right here, where there's a bunch of names and there's a bunch of unique types of dogs. But then just through the first iteration of this, they lost all the names, they lost two of the types of dogs, and that's your sharp decline, right? So we see that sharp decline in the data. And then over time, we keep losing information, we keep losing information until model collapse kind of converges onto this one point. Um, the same thing is shown in this figure about the second experiment. Um, so notice that this graph is is on a smaller scale. It's a lot more zoomed in because the effects were a lot less significant. But the same trends still occurred. There was a sharp increase to the first AI model, and then the perplexity sharply decreased to the second AI model, just like we saw above, and then it converged onto what we call model collapse. Um, so the trends are preserved, but this time it happened a lot less significantly over the same amount of time, implying that we can go for a lot longer without reaching model collapse. So a little bit of the math behind it. They use two uh, things to mathematically model collapse. Um, they used a discrete distribution and a multidimensional Gaussian approximation. That's just a bunch of probability. And then they did a more complex thing with density estimations in Hilbert space, which is just more complex probability. And the result is this equation down here. So basically what this says is this part says that your data will get as you do more and more generations of training your LLM on the previously generated data, as you do more and more of that, this the data points will get infinitely far away from the original data. So as the amount of iterations you did goes to infinity, the amount of um or the data gets infinitely far away. And then the variance goes to zero as you do more and more generations. The variance going to zero is all the data points being golden retrievers. So when every data point is the same non-coherent smudge, that's when the variance is zero. So in conclusion, we uh, showed that model collapse is when low probability events like the corgis are start to disappear, and the high probability events like the golden retrievers are overestimated and start to take over. There's a distribution shift towards those high probability events and away from the low probability events. It's important to maintain low probability events in LLMs because they are essential to the accuracy and reliability of the LLM as a whole. In a growing age of LLMs, eventually a lot of what we Google online will be AI generated. And we use the internet primarily as a source of training material for the next generation of LLMs. So if a lot of what's online is text generated, then it's going to slowly over many generations of LLMs lose its accuracy. And if we can no longer Google types of dogs and find all the types of dogs, and we can only find golden retrievers, then a lot of the use of Googling things is going to be gone. Uh, so, uh, in this growing age of LLMs, it also highlights the importance of human interaction. Um, if the text generated stuff is polluting the next generation of LLMs, then what we need to train the LLMs on is human interaction. So this paper really highlights the importance of that and suggests that we start to label text generated things as text generated. Um, Companies can do this in discrete ways that is non-invasive but detectable by their LLMs. Uh, this is a kind of an unlikely event because um, in order to dominate your market share as a company making an LLM, it would be advantageous to not label your generated material because then it would ruin the other LLMs and benefit yours. So it's going to be tough to get them to label their text generated data and maintain the human interaction on Google, but that's the future that we need to strive for, as shown by this paper. Thank you for listening. The links to the papers are down below. I suggest you read them. I think they're cool. Thank you.